Here is my third and final revision video on the topic of circle theorems. I would suggest watching part 1 and part 2 before looking at this one, where we're going to be concentrating on exam questions on this topic. Here are your 7 circle theorems. You need to learn all of these off by heart because in an exam question, they often ask you for a reason and you need to quote the reason for each circle theorem if you use it in the answer. Okay, so question 1. Here are all my circle theorems that you can look at alongside with this. You might want to have a look at question 1, each question yourself, pause it, and then see how I do the answer. They do get progressively more difficult. So this first one, hopefully you've completed it already. You've already had me on pause. So you should notice we've got a tangent. When I've got a tangent, I look straight to my tangent theorems, 5, 6, and 7. We've got a radius touching a tangent, so I know this is 90 degrees. It asks for your working out. How do I get this angle here? Well, it's just 180. Take off 90. Take off 72. Which would give an answer of 18. Okay, question 2. Again, have a look at all your circle theorems and decide which one you think it might be. So here we've got circle theorem number 2. You can see here we have an angle at a centre and an angle at the circumference. The angle at the circumference is half the angle at the centre. So BAC, it's referring to this angle here, is 33 degrees. And well, what's our reason? Have to quote this. Something along the lines of the angle at the circumference is half the angle at the centre. So the reason is the angle at the circumference you might just have the angle at the centre is double the angle at the circumference. 2 marks, 1 mark, 2 mark. If this next question, work out BOC. So I'm just going to join special lines on here. There's B, there's O, there's C. And again, if we look at this, well, we've got tangents here, a tangent touching a radius. So we know we've got a 90. I'm looking at theorem number 5 here specifically. We've got this one here is 90 degrees, and this one here is 90 degrees. We're told BAC is 40. You must show all your working. 360. Because angles in a 4-sided shape, and we have a 4-sided shape here, add up to 360. Gives us this angle here of 140 degrees. Question 4. Find the angle ACB. ACB, I've snipped that off slightly there, that is B. Hopefully you decided here to use circle theorem number 3. The angles in the same segment from a common chord are equal. So ACB, this angle here is the same as this angle. So it's 51 degrees. I'm going to shorten that statement slightly. The reason is angles in the same segment are equal. Question 4. 5 even. What angle ABC? Here we have a quadrilateral within our circle. So we're looking at number 4, the cyclic quadrilateral. Opposite angles add 180. So want the angle ABC, 180, take off 83 is 97. And my reason is opposite angles in a cyclic quad. Add to 180. So this is not an official circle theorem here. We asked for angle AOB. If you look through your circle theorems, none of these are useful. What I suggest you do is if you ever see a radius, so this is a radius and this is a radius, just put little marks on there, they're equal size. So we know that is an isosceles triangle, don't we? So we know this base angle here is also 48. So 180, take off 48, take off 48 is 84. And the reason here isn't a circle theorem as such, but we know because triangle AOB is isosceles. So question 7 onwards, you might have to apply more than one circle theorem. Look at question 7 again, we've got some tangents involved here, haven't we? So it's got to be a tangent theorem, I'm thinking. So if we look at 5, 6, and 7, we've got two tangents touching outside of the circle. So we know these are equal in size, right? We know this is an isosceles triangle. So 180, take away 46, divided by 2 gives you 67 for this angle here. And this angle here. So we could say, well, we want OAC eventually, so I'm going to put a little mark there and call it X. But I can say OAB. No, sorry, I can say CAB is 67 degrees. And what's my reason? Two tangents to a circle from the same point will be equal length. So the tangents to a circle. From the same point. I'm also thinking we might have another tangent theorem here. So you've got O to A is the radius. You've got a radius touching a tangent, right? So that's 90 degrees. So we can say that OAC is 90 take away 67, which is 23. And my reason is the angle between a radius and a tangent is 90 degrees. So I use that fact to get myself OAC. There is a different way you could have done this. If you've got your final answer 23 a different way, that's absolutely fine, as long as you've justified it in the correct way. Okay, question 8. So again, here, what do we want for part A? We want angle ACO. ACO, this angle here. Okay, so again, I've got a lot of tangent, well, I've got one tangent here, so I'm going to look at my tangent theorems. Got radius touching a tangent, radius touching a tangent here. So 90, take away 76. 14 degrees. And the reason is the angle between the radius and the tangent is 90 degrees. Part B, looking for ABC. Again, let's look at the tangent theorems here. So if you look at question 6, the alternate segment theorem, can you see you've got a tangent here touching a triangle. So this tangent touches this triangle here, touches that length of the triangle. So you look to the opposite angle to that length. And this angle here is the same as 76. So ABC is 76. And your reason is simply the alternate segment theorem. Two tangents touching outside the circle again from the same point. So we know those are equal, don't we? What are we looking for here? BAC. BAC. Give reasons each stage of your working out. Okay, so again, also we've got a tangent here touching this radius. That's 90 degrees, 90 degrees. So I might write that in somewhere. OBC. No, OBD. OBD equals OCD. And they both equal 90. And your reason is the angle between the radius and the tangent. Okay, so we've got a right angle triangle here, don't we? Angles in a right angle triangle add up to 180, which gives you this angle here is 64. Okay, COD. My reason is angles in a triangle. You can see this is symmetrical here, isn't it? That length is the same as that length. They share that length and the radii are the same. So we know it's symmetrical. So we know this is 26. And so we also know this angle here is 64. Then if you can see, if you've noticed this like arrow shape here, it's angles at the center and angles at the circumference, number 2. So angle COB is, well, 64 times 2, which is 128. And then we can say angle BAC (64). And your reason is angles at the circumference are half angle at the center. Just change that a little bit. Okay, question 10. Find the angle ABC. ABC. This is my unknown here. So we've got a triangle here. Might add in another length. Might add in this one here. Sometimes it helps to add in these extra length. I could see there's nothing we could really glean from there. So I've just added in this length because I know that is there 90 degrees. I know this is an isosceles triangle because we've got a radius and a radius. So this is 29. And so look, if you can see this triangle now here, you can see that the angle ACB, 90 plus 29. Then we've got angles in a triangle, add up to 180. So ABC. 180, take away 119, take away 29. Which is 32 degrees. Question 11. Find the value of x. You can see this will be using the alternate segment theorem. And I can also see that ECE is the same as this opposite angle here. So that's x unknown. I can also this triangle here. Angles in a triangle add up to 180, right? So we can say CAB equals 180, take away 61, take away 73, which is 46 degrees. My reason is angles in a triangle. And then I know that I can use the alternate segment theorem here, so I've got tangent touching a triangle. So x 46. And my reason is alternate segment theorem. Right, what do we want here? AOC, AOC. So I'm going to add in the line A to O. We've got an isosceles triangle, haven't we? ABC. You can see an arrow. We can also see an alternate segment theorem here. So this tangent touches the triangle here. So this whole angle here is 65 degrees. I also know this is 90 because I've got a tangent touching the radius. So 90, take away 65 is 25. I can say OCB is 25. And the working out would be 90, take away 65. OCB, OCB, this one here is 25. Isosceles triangle, isn't it? Also, because this is 65, this one here is 65. Let me just show you that with a different colour. That one there, 65, right? Which then gives you 65 take away 25. So OCA. $40, because it's from 65 take away 25. And that mini one there is 40 degrees. So that's 40, this is 40. It's an isosceles triangle. Because look, radius, radius. Just spotted a different way you can do this, but as long as you get the same answer as me, that's fine. So I'm going to just put on there, that's 40. You could have done this a different way, but that's fine. So AOC now. Angles in a triangle add up to 180, 180, take away 40, take away 40, gives you 100. AOC. So what you could have done here, so once you've figured out this was 65, you know that's 65, you could have got A, B, C, 180, take away 65, take away 65 is 50. And then because we're using this theorem number 2, the angle at the circumference is 50, the angle at the centre is double, so it'll be 100. You may have used that way. Okay, so for this one here, got a cyclic quadrilateral. Now, a mistake with this is to think that AOCD is a cyclic quadrilateral. It's not. The four corners have to touch the circumference of your circle. So this one here, and it's just our working, not our reasons. 180, take away 118, which is 62. And then angle at the centre, double the angle at the circumference. 124 degrees. Again, it looks like we've got the alternate segment theorem here, number 6. Got the tangent touching the triangle ABC. That's 53. The opposite angle is 53. This one here is 53. What are we even looking for here? ACO. ACO. This one. Angle at the circumference. Right, I do need all my reasons for this. So I can say CAB equals 53. My reason is the alternate segment theorem. And then I can say COB. Here we have a circle theorem number 2. The angle at the centre is double the angle of circumference, so double 53 is 106. Mark on my diagram here. We got here 90 degrees. Oh, yeah, let's use that actually. Hang on now. I'm going to get these two angles using my isosceles triangle because they're both radii. So 180, take away 106 divided by 2 gives you 37. This is 37. So we're going to say OCB equals 37. Isosceles triangle. And then I'm going to use the fact that I have a quadrilateral. No, I haven't. I've got a triangle here. Angles in a triangle add up to 180. Got these other angles. If I subtract all of those from 180, you'll get your answer. 180, take away 53, take away 27, take away 37, take away 37. 53, 27, yeah, okay, gives us 26. So ACO is 26. What's your reason? Angles in a triangle. add 2 or 180. Okay, 4 more to do, I think. Find the length BC. So that is from B to C. So I'm thinking, got a tangent touching a radius. I know this is 90 degrees. So OC, we can use Pythagoras, right? So 5 squared, A squared plus B squared equals C squared, right? O to C is your hypotenuse. (169) is C squared. Square root of 169 is 13. I know that length O to C is 13. I also know that's a radius, and this is a radius, which is 5. So a B to C, got to be 8. Because 13 take away 5 is 8. We've not used this circle theorem rule 1 yet. So we've got a diameter, which creates a semicircle. So this is 90 degrees. I know the angles in a triangle add up to 180. I'm going to simplify and then solve. Take off 90 from both sides. By both sides by 5. Which x is 18. Last 2 questions. Find BCD in terms of x. Give reasons for each stage. Circle theorem number 2, we've got an angle at the centre and an angle at the circumference. So, DAB, half x. And why is that? What is our reason? The angle at the centre is half the angle, the angle at the circumference. Half the angle at the centre. So I can call this half x. I also know, right? Got a cyclic quadrilateral here. Opposite angles in a cyclic quad add up to 180. Let me just get that reasoning first. So DCB or BCD is 180, take away half x. Final answer. Question 10. CD, it's an isosceles triangle. We've got our 90s here and here, right? We've also got some tangent theorems going on. AEC is x. We want OED. Okay, what can we say here then? We can say tangent touching this triangle. So they're using the alternate segment theorem. This is also X. Let me just show you that circle theorem, number 6. Okay, I've got an isosceles triangle. So if I do 180, let me just put that in actually. So I can say CD E equals X, and my reason is the alternate segment theorem. I'm going to use the fact we've got an isosceles triangle. So 180 take away X divided by 2 gives you the angles DCE and DEC. That just simplifies 2. If I divide both of those by 2, both those terms by 2, you get 90 minus half X. So I can say DEC equals 90 minus half X. Just mark that on in a different colour. Right. I want OED. Also, this one here is 90 minus half X, right? And the ultimate segment theorem shows that this angle here is actually the same as this angle. So that was also 90 minus half X. And then, because of this angle here is 90 degrees, if we do 90, take away 90 minus half X, we will get OED. I'm going to put this in brackets because there is a common mistake people make here. So 90, if I expand these brackets here, right, minus times 90 is minus 90. It's like saying minus 1 times 90. But minus 1 times minus half is positive a half X. 90 to be 90 is 0, so the answer is just half X. Okay, hopefully you understand circle theorems a little bit better. Thanks for listening.